Alright, so what we are going to discuss now is about dealing with the residue at infinity, which will make sense since we have been studying about the point at infinity, okay. And so let me tell you at the outset something that you have to remember which distinguishes between the residue at infinity and the residue at a finite point in the complex plane. The point is that the residue at infinity for a function which is analytic at infinity can be non-zero, whereas the residue at a finite point in the complex plane, okay, there is a point in the usual complex plane for an analytic function, the residue is 0, okay. So this is very, very important, okay. Of course, if the residue is 0 at a point, it does not of course mean that the function is analytic, okay. But the fact is that if you have an analytic function at a point, then the residue at that point is 0, so long as that point is a point of the usual complex plane. But if it is a point at infinity, okay, it may be analytic at infinity, but yet the residue may not be 0. So we are going to talk about residues at infinity, and we are going to talk about the version of the residue theorem on the extended complex plane, okay. So let me write this down. Residue at infinity and the residue theorem for the extended complex plane. So this is what we are going to talk about. So let me begin by recalling what the usual idea of residue is, okay. So recall if z0 is a point in the complex plane, okay, and f of z is analytic in a deleted neighborhood of z0, okay. So when I say this, I am saying that z0 is actually a singular point, okay. So it could be a removable singularity, which means that it is not really a singular point, it could be an analytic point, but on the other hand it could be a honest singularity, it may be a pole or an essential singularity. And then the residue of f at z0 is given by, well, residue of f of z at z equal to z0 is equal to, well, 1 by 2 pi I. So you integrate the function fz dz around a simple closed contour, a simple closed contour which goes around the point in the positive sense, okay. So basically so z0 is this point, and of course there is a deleted neighborhood of this point, sufficiently small deleted neighborhood of this point. So in particular there is a disk of sufficiently small radius, open disk surrounding that point, where the function is analytic, and then I am just taking a simple closed curve gamma, okay. Of course it is a simple closed contour, so simple means of course that it does not intersect itself, it has positive orientations, which means that it is going anticlockwise around that point. So in other words, the interior of the contour contains the point, okay. So the point lies to the left of the contour as you walk along the contour, okay, and the region to the left of the contour as you walk along the contour in the direction specified by the contour is called the interior of the contour, okay. And of course when I say contour, you must remember that gamma has to be piecewise smooth. So gamma is, whenever you parameterize gamma, mind you, gamma basically is a continuous image of an interval, okay. That is what a path is, but it can also be piecewise continuous image, okay. And well, in fact we always take gamma to be a continuous path. So but the thing is that it's also continuously differentiable at least piecewise, okay. That's the condition for a contour, and this much is required for this integral to be defined as a Riemann integral, all right. So this is the residue, and well I'm wondering I'm wondering if this that's right. So I was just wondering whether the factor 1 by 2 pi I is correct. It is. So for example, if I plug in 1 by z minus z naught, if I take the function f of z to be 1 by z minus z naught, if I integrate 1 by z minus z naught over a simple closed contour, sufficiently small contour, then I'm going to get 2 pi I, so the residue is 1. And see, of course it's very important that I choose this gamma in such a way that there are no other singular points of f inside other than z naught, and that is of course true because I am choosing gamma inside a deleted neighborhood of z naught where f is analytic, so there are no other points where f is singular other than z naught, okay. Now the point is, so this is the definition of residue, this is one definition of residue, and as you can see the importance of this definition is that if you multiply out the 2 pi I on the right side, if you multiply both sides by 2 pi I, what you will get is 2 pi I times the residue is the integral of the function over gamma. So what it tells you is that it tells you how to integrate a function around a singularity, okay. That's the important thing. So so the fact is that why is this definition interesting? It's interesting because you get to know how to what the integral of a function is around a singularity, okay. But the important thing is that you should be able to compute the left side without having to do the integral, okay, and that's the method of residues that you would have learned in the first course. And so there is so you also can recall the the usual definition of the other usual definition of residue in terms of Laurent expansions. So the point is that since f of z is assumed to be analytic in a deleted neighborhood of z naught, there is a Laurent expansion for f centered at z naught, and then you write out this Laurent expansion. It will contain both positive and 0 and negative powers of z minus z naught, and the residue is precisely the coefficient of 1 by z minus z naught, namely the z minus z naught to the minus 1, okay. So that's another so let me write that down. Recall also that if f of z is equal to sigma n equal to minus infinity to infinity an times z minus z naught to the power of n is the Laurent expansion of f around z naught, or f centered at z naught, or f about z naught. Mind you, that exists because of Laurent's theorem. Laurent expansion exists because of Laurent's theorem, and what's the big deal about Laurent's theorem? It's the analog of Taylor's theorem. So Taylor's theorem tells you that if a function is analytic at a point z naught, then you can expand it as a power series in z minus z naught, namely you can expand it as a series which involves only 0 and positive powers of z minus z naught. Laurent expansion tells you that you can do something similarly, something as good, even if z naught was a bad point, if z naught was a singular point and the only singular point in its neighborhood, then you can expand f in both positive and negative powers of z minus z naught, okay. So the fact is that if you're dealing with a singular point, you must allow negative powers of z minus z naught also in the series expansion. And of course, if z naught is a removable singularity, roughly, I mean, this is exactly what Riemann's removable singularity theorem is, that if you write out the Laurent expansion, you will only get a Taylor expansion if z naught is actually a removable singularity, okay, which is equivalent to saying that f is analytic at that point. So anyway, so the point is that if f has this Laurent expansion, then the residue of f of z at z equal to z naught is none other than a minus 1, And so so if I write this down, this is also equal to, as I wrote earlier, it's 1 by 2 pi I integral over gamma fz dz. Okay, so the advantage of this formula is that in many cases if I can write out the Laurent expansion at z0, then I can explicitly find out what this a minus 1 is, and that a minus 1 will give you that multiplied by 2 pi I is going to give you the integral of the function around that point. Okay, so that is the advantage of this, and you've used this in a first course in complex analysis to evaluate real integrals and so on and so forth, so it's a very useful thing. Now the point is that and then of course what is the generalization of this? The generalization of this is that suppose you are going to integrate a function around a simple closed contour and assume that inside that region the function has only isolated singularities, okay, there are going to be only finitely many isolated singularities, and then the formula reads that the formula that you get is essentially the residue theorem, which says that if you integrate the function around a bunch of isolated singularities, what you are going to get is 2 pi I times the sum of the residues of the function at each of those singular points. Okay, and that's the residue theorem. And here what we have written down here is that the integral of the function is 2 pi I times the residue at z0, because z0 is the only singularity, and the point is that this extends to 2 pi I times sum of the residues at various points, which are the isolated singularities of f inside the contour. Okay, so that's the residue theorem essentially. So the point is that it's in a way it's very easy. The residue theorem is very easy if you look at it like this. Okay, it's rather not a theorem, it's more part of the definition, except that if you want to really prove it, you will actually be applying Cauchy's theorem, okay, by surrounding each of the singular points by a sufficiently small disk and noting that outside this disk and inside your contour the function is actually analytic, okay, and you will have to apply the version of Cauchy's theorem for multiply connected regions, and you have to use this definition of residue to get the residue theorem. So let me write that down. More generally, if if f of z has only isolated singularities inside a simple closed contour gamma, and of course I am assuming that on the contour there are no singularities, okay, and is analytic on gamma. So this means that it is analytic on a small neighborhood, an open set which contains the contour gamma. So in particular I am avoiding the situation that there are singular points of the function on the contour, okay. Of course if there are singular points of the function on the contour, then at those singular points the function will fail to be continuous if they are honest singular points, and once the function fails to be continuous, it's very difficult to define the Riemann integral of the function over the contour. So you must understand that the moment you define the Riemann integral, more or less you are assuming that the function it has nothing wrong going on the contour, it's only what happens inside that matters, okay. So then there are only finitely many and integral over gamma f of z dz is equal to 2 pi I times the sum of the residues of the residues of f at these singular points. So this is essentially the residue theorem, okay. Of course that there are only finitely many follows from the fact that if you take the contour along with the, of course whenever I say contour, mind you, it's always an oriented contour, and without if nothing is mentioned, always the contour is oriented and it's given the positive orientation, which means that you go around the point in the anticlockwise sense, okay, and that is always always taken for granted unless something else is mentioned. So whenever integral over a contour is mentioned, you must understand that the contour is already oriented and the orientation is positive, okay. So so this is essentially the residue theorem. So let me write that down. So this is just the residue theorem, and well, as I told you, it's very useful to evaluate integrals integrals of functions around a contour which have only isolated singularities inside the contour, okay. So so this is it. Now the point is that what we want to do is that we want to do this for the point at infinity, okay, and we want a residue theorem for a domain in the extended complex plane. So how are we going to do it? So the idea is very simple. We start off by using this by adapting by literally using the same philosophy, namely the residue should be you integrate the function, okay, around the point, okay, and then divide by 2 pi I, okay, and then that should give you the residue. So so if you want to get the residue of a function at the point at infinity, first of all it should be analytic in a deleted neighborhood of the point at infinity, okay, and then I must take a contour that goes around infinity in the positive sense, okay, and I have to integrate the function around that contour, okay, and divide by 2 pi I, and I must get the residue at infinity, okay. So so the definition for a residue remains the same, namely you just integrate the function around by going over a contour that goes around the point in the positive sense as far as the point is concerned, and then you divide by 2 pi I, okay, that is the definition, alright, and let us see what that brings up. So I incidentally I wanted to point out something here which I just remembered. So let me tell you, for a moment, in a way, once you believe Laurent's theorem, that this is exactly I mean this formula is correct is something that you can more or less see, because so I have this expression of the Laurent series, okay, and what I need to compute is that I need to compute the integral of f over gamma, okay, and that's the same as integral over gamma of the series on the right side, okay, and now the point is that I can push the integral inside the sum, because the fact is that the Laurent series, like a Taylor series, wherever it converges normally. That means it converges uniformly on compact subsets, and since I am going to integrate over gamma is, of course, mind you, any simple closed contour is a compact set because it is both closed and bounded. So therefore the integral of the sum is same as sum of the integrals, so I can push the integral across the sum, and when I push the integral across the sum, what is going to happen is that you will see that if I take positive powers of z minus z0, the integrals are going to vanish, because the positive powers of z minus z0 are analytic functions, and Cauchy's theorem is going to tell you that whenever you integrate an analytic function around a simple closed contour, you are going to get 0. In fact, the positive parts are all entire functions, okay, they are just polynomials, and the same thing is going to happen to the constant term, okay, and then if you take the negative powers of z minus z0 greater than 2, okay, so I mean what I mean by that is, if you take terms involving 1 by z minus z0 the whole squared, 1 by z minus z0 the whole cube, and so on, the integrals of those terms will also vanish. That is because they all have antiderivatives. So it's something very basic that I want you to understand. The fact that an integral vanishes is basically it's equivalent to saying that the integral is independent of the path, and especially when the integrand has an antiderivative, then you know that the integral is actually the final value minus the initial value, okay, of the antiderivative, and if the final value is equal to the initial value, which is what will happen if you go around a closed path, you are going to get the integral to be 0, okay, and so you know, all the integrals which involve z minus z naught to the power of n, where n is -2, -3, -4 and so on, they are all going to vanish. So the only thing that is going to survive is going to be integral over gamma a minus 1 ez minus z naught power -1 dz, okay, and you know the integral over gamma z minus z naught to the -1 dz is just going to be 2 pi I, and that's just because of Cauchy's theorem, because the integral over gamma is not going to really depend on the shape of gamma. You can replace gamma by a small circle, okay, going around z naught, and then you actually parameterize the circle as usual, write it as z equal to rho e to the I theta, theta varying from 0 to 2 pi, and compute the integral, you get 2 pi I, okay. So therefore what I want to tell you is that once you know Laurent's theorem, okay, once you believe Laurent's theorem, this formula for the residue that a minus 1 gives you the residue is more or less direct, okay. So that's something that I want you to recall. Now let me go back and define the residue at infinity. So suppose f of z is defined in neighborhood of infinity, okay. So mind you that what this means is that f of z is defined on a circle, on the exterior of a circle of sufficiently large radius. That's what it means. A neighborhood of infinity is by definition, you know, by the stereographic projection, the same as the exterior of a sufficiently large circle, okay. And so at this point what we do is that we define the residue of f at infinity to be just the integral over gamma 1 by 2 pi I integral over gamma f z dz, where gamma is a simple closed contour that goes around infinity in the positive sense, okay. This is exactly the way we define it as we defined it for a point in the usual complex plane, okay. So let me write that down. Then residue of f of z at z equal to infinity is defined to be, so I put a colon and equal to 1 by 2 pi I integral over gamma. So you know, let me change notation to fw, because I will need to appeal to something else, namely I need to appeal to changing the variable to 1 by z. So let me do that. Oops. So fw w equal to infinity 1 by fw dw, okay, 1 by 2 pi I integral over gamma. So where, so let me write that, this is very very important, where gamma is a simple closed contour going around the point at infinity in the positive sense. So you know, this is the definition, and well, you know, so this is exactly the definition that you would have made for a point in the complex plane, and this is the same definition I am using for a point for the point at infinity. But then there are 2 or 3 things that one has to be careful about. The first thing is that what do you mean by a contour that's going around infinity in the positive sense? So the fact is that you know, you must think of a contour so here is where you again appeal to the stereographic projection, okay. You know that a sufficiently small neighborhood of infinity is given by the exterior of a sufficiently large circle centered at the origin, okay. So in some sense a sufficiently large circle centered at the origin should be a contour which goes around the point at infinity, okay. And you can see this so more generally, if you take a sufficiently large contour which goes around the origin, okay, a simple closed contour which goes around the origin, sufficiently large means that it encloses a sufficiently large area, okay. Then for that matter, I mean, it lies in the exterior of I should rather say it lies in the exterior of a circle of sufficiently large radius, okay. Then that itself is an example of a simple closed contour that goes around the point at infinity, and that's because of the stereographic projection. And the only thing is that what is this business of the positive orientation of that contour with respect to infinity? Mind you, the positive orientation means that infinity should lie in the interior of that contour, okay. So you should orient the contour in such a way such that the interior of the contour contains a point at infinity. Now you know, if I take a circle, sufficiently large circle centered at the origin, and orient it the usual way I did, which we do, namely give it the anticlockwise orientation, then the origin becomes comes into the interior. The interior just is the interior of that circle, okay, and the exterior will be the exterior of the circle, and that will contain the point at infinity. So you can see from this argument that you will have to orient it clockwise, okay. So so gamma must be a simple closed contour lying in a sufficiently small neighborhood of infinity. So it should be lying in the exterior of a circle of sufficiently large radius, and it should be given the clockwise orientation. That is what it means, okay. So let me write that down. This means that gamma should be a simple closed contour in the complex plane lying outside a circle of sufficiently large radius, but given the clockwise or negative orientation. So here you see, you have to be careful. I am saying that gamma should have negative orientation here, but in the statement before that I am saying it should have positive sense. So mind you, in the statement preceding it was positive sense with respect to the point at infinity, and positive sense with respect to the point at infinity is negative sense with respect to the origin, okay. So these are not contradictory statements, okay. You have to understand this subtlety, and well, of course you can also see this pictorially more or less. See, you know, if you draw the stereographic projection, so here is the xy plane which is a complex plane, or the z plane, and then you know, we draw this third axis which we call it as u, and then you take the unit sphere, surface of the unit sphere in 3 space. I am going to get something like this, you know, this is the stereographic projection. So you know, if I take now, you know, if I take sufficiently if I take a circle on the complex plane of sufficiently large radius, okay, and then you know, well, you know, the point at infinity corresponds to this point here on the stereographic on the Riemann sphere, which corresponds to the north pole. So this corresponds to the point at infinity, okay. So I put this triple line to tell you that it corresponds to the point at infinity under the stereographic projection, and well, you know, what happens to the well, you know, the exterior of this circle, the exterior of the circle in the complex plane, that is going to correspond to, well, on the Riemann sphere is going to correspond to this small disc like region, though it is a curved surface, it is a small disc like region. When I say disc like, I mean topologically, you can flatten it to look like a disc topologically, and it is a disc like neighborhood of the north pole on the Riemann sphere, okay. And that is how the shaded regions on the plane, namely the exterior of the circle and the small cap on surrounding the it is like a polar cap, okay. If you imagine the earth, it is the north at the north pole. So now the point is that, you see, what you must understand is that if I now give these if I now give this so in particular, you know, if I now take a sufficiently if I take a contour which lies in outside this circle, okay, if I take a contour like this, now that contour is going to correspond to a contour here on the Riemann sphere that goes around the point at infinity, okay, and as I make this circle bigger and bigger, that's going to give you a smaller and smaller contour, simple closed contour that goes around the point at infinity. The only thing that you have to worry about is the orientation. The orientation, the way I've drawn it, the orientation should be like this. Mind you, it is actually clockwise about the origin, and the reason for that is that if you define it like that, which is what you should do if you are dealing with a point at infinity, then the interior of that contour is the exterior. So this region, this thing outside, this is the interior of that contour, okay, and well, it is actually the region that lies to the left of the contour as you walk along the contour, okay, and you can see that this region corresponds to, well, this region on the Riemann sphere, and that of course contains the point at infinity. So the point at infinity is an interior point for the contour oriented in the clockwise direction, okay. So you can see this diagrammatically, okay, fine. So very well, now that we have defined what the residue at infinity is, so of course this is gamma, right. So let's compute it. Let's compute what the residue at infinity is. So f of z is, well f of w, well let me write f of w. F of w is going to be sigma n equal to minus infinity to infinity a n w to the n. This is the Laurent series of f. This is a Laurent series of f in a neighborhood of infinity, okay, and mind you, in principle it is actually also the Laurent series of f at the origin in some sense, centered at the origin, but in a domain that's a neighborhood of infinity. And the only thing that you distinguish is that when you say it is a Laurent series at infinity, you see the singular part is the one that involves the positive powers of w, and the analytic part is the one that involves 0 and negative powers of w, because it's the negative powers of w that behave well at infinity, okay. So that's the only difference, but what you are actually looking at is actually the Laurent series of f at the origin, okay. Now but anyway, the fact is, for the same reasons that I told you earlier, if you compute if you compute integral over gamma fw dw, if I do this, what I'm going to get is and you know, of course I think as a 1 by 2 pi I, this is what it is, well you know, mind you, if I compute this integral the way I normally would compute the integral on the plane, what I'll first do is I always compute integrals with my contour being positively oriented with respect to the usual plane, that is with respect to the origin. So what I'll do is I'll first write this as minus 1 by 2 pi I integral over minus gamma, where minus gamma is the gamma oriented in the anticlockwise sense, and that is the positive sense for the plane, okay, with respect to the origin if you want, okay, and then I'll get this, and you know, now if I plug in the series here, okay, and remember that I can do integration term by term because of the same reasons I told you earlier, because the Laurent series always converges normally, it converges uniformly on compact sets, and gamma or minus gamma for that matter, they are as sets, they are compact sets. So if I do that, again what is going to happen is that what's going to survive is only the coefficient of 1 by w, okay, and that's going to give me that's the coefficient when n is minus 1, so I'm going to get a minus 1. The only thing is that I'm going to get a minus a minus 1, okay. So what you must see is that what you'll see is that I'll get 1 by 2 pi I times 2 pi I times a minus 1, this is as before, and I get minus a minus 1, okay. So so you see, so the moral of the story is that when you are looking at the residue at infinity, okay, what you do is you literally get minus of a minus 1, okay, which is with an extra minus sign added to it, okay, whereas if you look at the usual Laurent series of a point around a point in the complex plane, then the residue is actually a minus 1, which is just the quotient of the first negative power of the variable, okay, whereas in this case it is the minus of that. And so you can now believe that you can see right from here you can see something happening. Suppose this function f had only singularities at the origin and at infinity, okay, which means that this Laurent series has infinite radius of convergence, okay. So by that I mean the Laurent series is valid for all w not 0 and not infinity, okay. So it's valid on c star, c minus the origin, okay. If that is the case, then you see this function, if you calculate the residue at the origin, you are going to get plus a minus 1, okay, which is the usual definition of residue. If I take this function, suppose it's also analytic in a neighborhood of the origin, okay, and suppose the only singularities are at the origin and at infinity, okay, then you notice that the residue of the function at the origin is plus a minus 1 and the residue of the function at infinity is minus a minus 1. What is the sum of residues? It's 0, and that's exactly what the residue theorem says for any function which has only isolated singularities in the extended plane, okay. So the statement is that you take a function which has only isolated singularities in the extended plane, okay, which means that there are only, mind you, it means whenever you say isolated singularities in the extended plane, there have to be only finitely many. That's because the extended plane is compact and any subset of a compact isolated subset of a compact set is finite in this case, okay. So therefore what the residue theorem will say is that if you take the residues at all the points in the finite complex plane and you take this residue at infinity and you add them up, you will get 0. And here that's exactly what happens if f were having a residue, if f was having a singularity at the origin only and a singularity at infinity, okay, then you see that from this computation the residue at 0 is plus a minus 1, the residue at infinity is minus a minus 1, the sum is 0, okay. So anyway, so the moral of the story is that it gives you a very easy way of computing residue at infinity. It's very, very simple. What you do is that you simply write the Laurent expansion of the function about the origin, but write it so that it's valid in the exterior of a sufficiently large circle, okay. Mind you, you must always remember this, that so this is probably maybe I should spend a few minutes on this. See, in a first course in complex analysis, when you study about Laurent expansion at a point, you must remember that there are several Laurent expansions, there could be several Laurent expansions at a point. That's because the Laurent expansions, the domains of the Laurent expansions are actually annuli whose boundaries contain the singular points, okay. So if I talk about the Laurent expansion of a function at a point, okay, it could be even a analytic point, doesn't matter, but the problem is that because there are singularities, there are other singularities, the Laurent expansions will be different expansions because you will get different annuli, okay, and therefore when you write the Laurent expansion at the origin, you should not look at the Laurent expansion at the origin that may be valid in a deleted neighborhood of the origin which is at whose boundary there is a finite singularity. You should not look at that. You should rather look at a Laurent expansion that's valid outside a circle of sufficiently large radius, okay. Write that Laurent expansion. That is the Laurent expansion that you need to work with infinity, okay. And in that Laurent expansion, look at the again look at the coefficient of 1 by the variable and take it to the minus sign. That's the residue at infinity, okay. And that's how you can very easily write out you can compute what the residue at infinity is, and that combined with the residue theorem is another powerful tool for computing a lot of integrals, okay, as we will see in the next lecture.